First of all, I would like to thank the organizers for inviting me, because it was very fruitful for me also to, in the last 5 days, then I also met with the new people, my colleagues. I have not, I didn't know it earlier, and also the students. And this challenge workshop also has beneficial for me too. And that there were many other things that I didn't know it. I learned here. So I was asked to give an overview for the traveling wave tube. And I will not talk about the historical mathematical aspects of the traveling wave tube, TWT. Aga, another friend of mine, he will talk about it all the time. I promised myself not to show any equations in my speech because I was tired of the equations. To be honest, I am sure you are too. But at this one occasion, I will show to prove or to show why slow structure wave slows down the electromagnetic wave. That's important. But when I am preparing my talk, I realized that the vacuum, the name of the workshop is the what's called vacuum electron devices. I have come to realize that the vacuum is a very important concept. Therefore, I wanted I wanted to delve into the vacuum before telling you about traveling wave tube amplifier, because it is utilizing the vacuum. And vacuum in the history of science has very important concept. We don't realize it. We get granted right now because it's very simple for us. But in the history, it was not like that. Our understanding of the vacuum, the vacuum is defined in two different ways. There is a classical vacuum, we define as the region of space without matter, and also there is a definition of vacuum in quantum mechanical way. That's another concept. From our perspective, the classical definition of the vacuum, as defined as the region of space without matter, is first conceptualized before the Christ, around the 5th century, 460. Democritus and Lycopus proposed. We know the Democritus proposed the matter consists of atoms. The smallest unit of the matter is atoms, and atoms cannot be divisible. And also, he assumed that these atoms to be spherical. You may ask why it's spherical, because the spherical is has the most symmetry in it. In the ancient times, the people, when I say the ancient times, I am talking about the ancient Greek philosophers, because the history of the science is narrated by the Western scientists. Therefore, they go all the way back to the ancient times, and they don't mention the history of science in Middle East or in India or in China, in other parts of the world. But the concept of the vacuum is important. They, at that time, the people of the philosophers, at that time they called the philosophers of the Greek, ancient Greek, they conceived the world consists of 4 types of matters. Earth, right now we call it solid, and water, we call it liquid, and air, we call it gas, and fire, we call it plasma. That was their conceived. From our perspective, these are the 4 different phases of the matter. There was a problem of how many times we can divide the matter. Is it continuously can be divisible, or it comes up to one point and no longer you cannot divide it? So Democritus proposed that the matter consists of atoms, and atoms cannot be divisible, and they are spherical shape. If you put the objects of spherical shape into a region, there are emptiness around it. That's called the void. Therefore, nature consists of the atoms and the void. But it's interesting thing. Aristotle is a towering figure, like the Einstein of the 20th century. He was authority, and he opposed. He said the nature abhors a vacuum. Nature dislikes a vacuum. It doesn't accept a vacuum. It doesn't allow to a vacuum. It's the horror vacua, the Latin shape. This Aristotle's understanding of the nature has taken 2,000 years. Nobody, I don't want to say not questioned, but people accepted there cannot be void or vacuum. And he stole the science. It prevented the humanity benefiting from the applications of the vacuum. Even Islamic philosophers, Al-Farabi also debated about the presence of the vacuum, but they didn't come with any proof. In the 17th century, as we know that the Renaissance has started in Europe, and they were questioning everything, and the scientific understanding of the world shifted from contemplation to the experimentation. They were testing everything, and the scientific thought and scientific method were also developed in that age. In the 17th century, in the beginning of the 17th century, even the Galileo worked on the concept of vacuum, but he was unable to prove it. Based on his studies, in 1643, Evangelista Torricelli, the famous Torricelli, who gave us the barometer, proved that he was trying to prove that the air has a weight. Because after his time, Bernoulli equations were written, and Bernoulli equations, if you have a column of water, it should be balanced by another column of water or by something else. He was trying to prove that the air was applying a force or weight, they called the weight, to balance the weight of the column of water. He made many experiments, including water and with other liquids. All that failed, because he didn't know that. Right now we know it. He needed 10-meter long of pipe, at least. And they didn't have a 10-meter long of pipe of glass. It had to be a glass because you have to see what is going on inside it. If you use an iron pipe, you never know what to have inside the pipe, the secret. He used a glass tube, meter of size. The interesting thing, in his time in Italy, in the area of Venedig, there was a factories of glass. They were making windows, colorful windows for the churches and for the houses. There was a glass industry. You know, the glass consists of the silicon, and there was another materials cut it. It was easy to shape it, and by blowing, they were giving any shape they wanted. Yeah. In his time, therefore, it was easy for him to reach to the glass pipe of not any length, but at least certain length. He had a clever idea of using water or other liquids, which failed. He decided to use the mercury. Mercury is a liquid metal, not a liquid metal. He filled a pipe with the mercury liquid, and inverted into the dish. They call it dish or mercury sink. What he has seen is that the amount of mercury within the pipe dropped down up to 0.76 meter or 76 centimeter or 760 millimeter. It's called 1 torr as a unit. He proved two things. First thing, he proved the atmospheric pressure, that the air had a weight. counterbalancing the weight of the mercury in the tube. And also he proved that above the mercury, the emptiness is the vacuum. This concept, it was the first time the vacuum has been created. Otherwise, think of a pipe, the pipette, what we call it. If you suck the air from one side, air comes from the other side. If you close the other side, if you keep sucking, the pipette collapses. We all know about this. Yani, nature was not allowing the presence of the vacuum because of the air pressure. Right now, we can say that one. At that time, they didn't know it. This was very important, and from my own perspective, the change of paradigm. It's called the paradigm. It determines how you think about how you look at the things, and therefore he disproved and the vacuum denial, Aristotle, and the people started using the applications of this Torricelli barometer or the vacuum. For example, Pascal, the famous Pascal, confirmed that the mercury height changes with the altitude. He proved that because if the mercury height is changing with the altitude, it means that the weather is going weaker and weaker or less denser if you go to the high altitudes. And after a certain point, there would be no matter. This one you can see over here in the shape at that time. And also, this barometer allowed the people to predict the weather patterns in advance. Çünkü when the weather changes, when the rain comes, or storm comes, atmospheric pressure was changing. Always, therefore, the height of the mercury was changing. It was important for the sailors at that time and for the people. And also, subsequently, 1960, the people started developing air pumps. Up to that time, they conceived air pumps. The air pumps consist of a piston and valves over here. And also, there is a public demonstrations. All we know from the high school books. There's a famous Magdeburg hemisphere experiment. Two hemispheres connected to each other, and Magdeburg sucked the air inside it and tied to the horses in front of the people, and the horses couldn't separate these two hemispheres, showing that how powerful is the atmospheric pressure. And Boyle and Hooke refined the vacuum pumps and the laws. Boyle come up with the laws of the gases and pressure and the volume where pressure multiplication is a constant, but the pressure is inverse proportional to volume, something like that. He came up the first laws of the gas system. It is important. And also in the 18th century, 19th century, it was used in the vacuum was used to prove the existence of the electrons. Then, as the famous cathode ray tubes. Then, J.G. Thomson utilized this cathode ray tube up to yesterday. We were using for still we are using for oscilloscopes and the television tubes. Then. There was a filament and the electrons coming and deflecting coils and phosphorus screen. That is the beginning of the TV. But initially it was used for experimental purposes. This is happened in the 19th century. At the same time, Thomas Edison created the light bulbs, converts the electrical energy into light. That was one of the historic moments in the human history, because he brought the light to the civilization during the night. We now take it for granted. We don't understand its value, because at those times, the lightning during the night times were only by burning the oil and the fat, and they were hunting whales most of the time, but they were using their fat in the cantron, they call it, something like that. During the night time, it was very dark, unless there is a moon shining over there. It is a very important moment in the human history. He come up, this is the picture he applied for one of the patents. There is a filament, and the interesting thing, when he come up with the light bulb, he enlightened the New York City system. There was one problem. His light bulbs were breaking down, very open. Later he realized that it was the material he used, tungsten or carbon fiber, were oxidizing by the air, what we say right now. At that time, he thought that it is because of the air, and he decided to evacuate the air from the bulb. It is said that the first time he used the mercury drop technique, the Torricelli used to create a vacuum. Then he came up with the long-lasting light bulbs. The interesting thing, the irony, the sales of the light bulbs dropped the next year because it was cheap. Those people who can afford to buy the light bulbs, they bought it, and there was no people. And since they were not breaking down, the lifelong light bulbs, the factories started losing money. In the 20th century, there were 4 or 5 factories producing the light bulbs. They come together and they decided, they made an agreement among themselves to restrict the lifetime of the bulb to 1,000 hours. Usually less than 1,000, but they say 1,000 hours. Even they find each other. They made the agreement. If anyone violates the agreement, he will be fined. That's interesting. Another interesting thing, because it started at the beginning of the electronics, that's the reason I am emphasizing on this one. Edison was in favor of the direct current, and he was using direct current. He realized that his light bulbs, on the one side of the light bulbs, changing color. Then at that time, the people were talking about, or some scientists were studying on the thermionic emission. Since he was using direct current, one side is cathode, the other side is anode. Cathode part had the electrons out of it because of the thermionic emission, and it interacted with the light bulb, that side of the light bulb, and changed the color. This is important because it led the way to the diode, one-way electricity. This is one of the most important elements of the electronics. Another is the transistor. After that time, electronics consists of the condensators and coils. This is the picture. I brought it on one for you. This is something like this. This is a cylindrical diode, what they call it. Cathode side is the heated, and the electron was flowing to from cathode to anode, because heating in the vacuum created the thermionic emission of the cathode, and it allowed the electrons pass from cathode to anode. but reverse is not possible. If you change the polarity, make the plus minus and the other is a plus, the electric is not flowing. Therefore, it opened the way for one-way electricity. Up to that time, electricity was going both ways over the wire. This way, you were able to direct the electricity only in one direction of the wire. After that, so many other inventions came out. The most important one is the triode. I will talk about it. Vacuum triode. Another inventor, he realized that he can moderate the electron flow by putting a grid between the cathode and anode. This was an amplifier, signal amplifier. Another most important element of the electronics invented this way, and many other, they call it the tridode, tetradode, pentadode. There are many other variations of it, as you see. But what is important for us right now, what we are using is a transistor, what we call it right now. These are the type of transistor bulbs. These are all made possible by vacuum. And age of electronics has started. Before that, there was electricity, electrical engineers. But after the invention of this, within 2 years, vacuum diode and vacuum transistors. In fact, there was a need for the vacuum transistor for amplification. The reason, at that time, the Graham Bell developed the telephone lines and telegraph lines, but there is range goes up to 380 miles. Behind that, the signal was attenuated and there was no communication. Therefore, the west side and the east side of the United States is 3,000 kilometers, 50,000 miles. They were no communication, direct communication. Using these amplifiers, electrons, transistors, communication started, and many other inventions came. The vacuum chamber also is important. It changed our understanding of the atom, the physics. Up to that time, in 1911, 200 years ago, all the scientific community were thinking that the matter was consist of plus and minus charges, and they were evenly distributed. Evenly distributed. Ernest Rutherford, in his famous experiment, he changed our understanding of the atoms. He showed that the positive charges were localized in the center, and the negative charges are flowing around it. This was made possible by the vacuum chamber. Why? Because he was using alpha particles. They call the alpha particles. We know the right now helium nuclei coming from the americium radioactive element. Alpha particles cannot propagate in that space, in the atmospheric conditions. It goes only a few millimeters, then interacts with the air. But in a vacuum chamber, it can propagate to further distances. Therefore, he was able to make his experiment via the vacuum chamber. If there was no vacuum chamber, our understanding of the atom will not be different than the 100 years ago, let's see it. And we will not be able to progress it. Atomic model gives us the quantum mechanics. That's the interesting thing. When he came with his atomic model, but it there was a problem. Electrons are rotating around the center, positive charges, and the rotation is accelerated motion, and electrons was supposed to radiate because of the classical mechanics, the Maxwell equations, and Newton equations altogether indicates that the accelerated particles, charged particles, radiates. Yani, radiates electromagnetic waves and loses energy. Since in that model, the electrons were not falling into the center, the Niels Bohr come and quantize the orbitals of the electrons, first quantization, and he was able to produce the spectrum of the hydrogen atom by that quantization. It started the quantum mechanics then, the modern understanding of quantum mechanics. Then quantum mechanics gives us the silicon-based modern electronics. Make the vacuum tubes obsolete in one sense. Yeah. Vacuum tubes gives us communications. Still we are using, especially long-range communications. We use the vacuum tubes. Vacuum tubes gave us the transistors, as I told you. The interesting thing, transistor tubes gave us the computers. So the reason, at that time, the computer were realized in a simple form in terms of the relays. Then, what they call the relay is a solenoid bobbin, and there's an iron encoded, and there's a handle over that. If you apply the electricity, it opens and closes. On the other side of the electricity, and light turns on or turns off. That's simple. Abstract, simple device allowed to add the 1 and 1, 2, for example. Simple to addition. It was not so practical to bring all the relays all together and to make them together. They replaced these relays with the transistors, because transistors also act as a valve, as a switch. And it gives us the computers. That's the first computers were made at that time in terms of the bulbs. And of course, transistor bulbs also breaking down in time. And at that time, the first computer made to work 160 hours, something like that. And also that those computers gave us the atomic bomb and the nuclear energy, because they needed to calculate the critical mass needed for the atomic bomb. It was not possible to make those calculations by hand. They made those calculations using this computer, the first computer. Therefore, I say that every important development in modern science has its origin on the vacuum application of the vacuum tube system. And also, we changed the way we do experiment. Right now, in higher energy physics and nuclear physics, you cannot do any experiment without a vacuum. Even the chemistry, no, not chemistry, in solid state physics. Always we are utilizing the vacuum. In summary, ancient times, vacuum was denied. At the Renaissance, the first vacuum experiments were done. 17th century, the law for the gases are Boyle's law, and the cathode rays electron discovery came out. And late century, Edison's vacuum bulbs, practical vacuum use started. 20th century, we have the electronics and the communications, all other things. All these developments owe its origin to the concept of vacuum. Sometimes I say that, let's suppose that we met with the vacuum 2,000 years ago. We started utilizing the applications of the vacuum 2,000 years ago. Our development would be much further than right now. Because Denial of the vacuum stalled the scientific development related to the vacuum 2000 years from the BC minus 400 to 1600, the time of Torricelli, about 2000 years then. The vacuum is such an important concept. Right now, the subject of this workshop also is related to the vacuum. We are talking about the certain applications of the vacuum for the amplification of the signals. I will tell you one thing that's important. This is very common. First thing is known well, but the second is not known well. Necessity is the mother of all inventions. All inventions in the past has its origin on the necessity of the society. There was a need for it, for that development. Therefore, someone came up with an invention to satisfy that need and also to earn money. Curiosity is the mother of all knowledge. Scientific people should be very curious people, because curiosity will lead them. They don't think any applications of what they study. Only the engineers has to think about it, about applications of their study. The one thing you should know it, even I know, I learned at the very late ages, and another friend of mine, he graduated from the MIT and he's a professor in the Kent University. He paid a very heavy price for that one. This is an anecdote, but let me tell you. I always forget his name. He's a good professor in electrical engineering. He's one sense, is the father of the 5G. He developed a polar code, a kind of coding the information for telecommunication purposes. And Huawei firm made it into product, developed it, that code, and developed the 5G before the Americans. And there was a crisis between America and China. My friend, the important, if you come up with a new knowledge which may have applications, before you publish it, you should patent it. If you don't make a patent application, if you go through the publication, you cannot. The patent officers cannot grant you patent, because any public knowledge cannot be patented. There is a fundamental principle. Therefore, either you pursue science or engineering. If you come up with an idea which may have practical applications, you should apply for patent before you make it published. Later on, you can publish, but first to claim it. Before you claim it, if you publish it, like my friend, you lose it millions of dollars, maybe billions of dollars. Because in every phone, these are not 5G, but it's coming to 5G. Their patent revenues, $50 or $60 or $100 per phone, are being paid for the patent rights. You can imagine that if he has taken the $10 per phone, how many $1 million? Because on the earth right now, more telephones than the human beings. If there's on approximately 7 billion human beings, there is about 8 or 9 billion telephones produced. Erdal Arkan, yeah, you're right. He was my friend in MIT. I asked him why he didn't apply for patent. He said he didn't know it. He was right. I didn't know it too. When he returned to Turkey around the age of 30, something like that, but he didn't know it. He was a scientist. He was doing his research and making publications and educating the students. He never thought about the patent. But in the United States and in Europe, it's not like that. If someone has an idea which may have commercial applications, not his university facilitates his application to the patent office. He helps him to get a patent, and university take care for his part also too. Therefore, as engineers, if you ever come to with a new idea, you just apply for a patent. Application is not expensive. Getting a patent has a little bit price, but applying is good enough, because granting the patent takes more than 1 year. Within that time, either you get the patent or you can sell it to interested parties then. There is in Europe there are the law offices specialized in patent rights, because they earn money. They take a portion of the revenues. Therefore, you don't pay anything at all then. Now, I will come to the TWTA, traveling wave tube amplifier. Before the traveling wave tube amplifier, the magnetrons and klystrons were developed based on necessity. Magnetrons were developed in England by Fleming, the engineer, electrical engineer, because there was a need. That was during the wartime, the World War II. The German airplanes were coming and bombing the London all the time. The British didn't have early warning systems. And even they sent the people to the other side of the Manche Sea, to the France area. They were looking with the binoculars, the German planes, whether or not they are coming, and they were signaling to the London. But it was not working, because sometimes the weather is rainy and during the night time. So they needed another way of detecting the objects from a distance. So, therefore, they needed the millimeter-sized electromagnetic waves. That was how the magnetron came out. During the war times, the British couldn't develop it further, and they transferred to the Americans. The Americans, first they didn't believe it, but later on they made it work, and they gave the advantage to the Allied forces, the Americans, British, against the Germans during the World War II. Why? Because they installed into the airplanes and to the ground, and German airplanes were detected from far distance. Even the German pilots were aware of the American planes. They ambushed the German planes, and the Americans had the advantage in the space, in the air. In a war, if you have an advantage in the air, if you control the air, you can win the war. That's the reason Mustafa Kemal said, the future is in the sky. Biz bayız göklerdedir. Yani the security of a country is based on how they can control their airspace. If you can control your airspace, including up to the space right now, because there are missiles and other things coming. If you can control the airspace, you can secure your country. Otherwise, you will lose. That was the reason that the radar was developed. It was developed in MIT. There. Important thing. Now, when it comes to the TWT, the klystrons or magnetron has a very narrow band and is frequency dependent. What it means? The structure depends the frequency. The cavities depends the cavities makes cavity volume or cavity sizes the frequencies are dependent on the cavity sizes, let's call it. It's very narrow frequencies they can amplify. At that time, there was a need for high power and wideband applications of electromagnetic waves. The reason the Rudolf Kalkner, this TWT studies, the TWT amplifier studies started around the 1930s, but developed during the wartime. Kalkner, there was a need also at that time again. Radar jamming or communications jamming. Jamming is to prevent it, communications between two interested parties. You are just creating electronic waves in every frequency, in the noise, creating a noise, and you can prevent the communications, and also radar jamming, fooling the enemy pilots or other systems. It was needed. Therefore, frequency independent, large band, and high power amplifier were needed. Rudolf Kalkner started this study because he was an engineer in the Electron laboratory working on the radar research program of the Army. He analyzed the Electron and the magnetron. He saw that the narrow band and low gain, and he needed wide band and high gain amplification. He saw that either magnetron, circular, and Electron. You didn't see the Electron is a straight one, which has the cavities. Cavities are discrete, but structure is a periodic. Cavity, non-cavity, cavity, non-cavity. It goes periodic, but a discrete structure it has. He thought that if he has a continuous structure, periodic but uncontinuous structure, he can get high power and possibly wide band amplification, because cavities restricted the amplification to certain frequencies. Cavity resonance is what we call it. For example, magnetron thing. Electron is rotating. When it comes to the cavity, it loses energy. When it passes the cavity, comes to the vein, what they call the vein, it gains energy, loses energy, gains energy. It goes in this way, in a discrete manner. In Electron is a straight structure, cavity, vein, cavity, vein, cavity, vein. There is a both cavities symmetry. The electron comes in a straight way, loses energy, that energy converts into electromagnetic wave. Then there is a drift region. There is nothing happens in that region. And again, it comes to the cavity, sees the electric field, and loses energy, again drifting. Therefore, Kalkner, looking for a continuous but a periodic structure. That structure was the helix. The helix was with a coil. You take the wire and drop it, and it's a helix for given radius and even pitch, you can make it that one. The question is, how we came to that idea that the helix would satisfy the need. The interesting thing is here, helix structures, continuous and periodic structures, slow down the electromagnetic wave, traveling wave. The waves are traveling with the speed of light. We cannot interact the electrons with the wave traveling with the speed of light because we cannot increase the electron's energy up to the speed of light. The only way to interact the electrons with the electromagnetic wave to reduce the speed of light of the electromagnetic waves. If they match into each other, we call it the resonance, then one transfers energy to the other. Electron transfers its energy to the question is how the Hofner came out with the idea of the helix. Why he thought about the helix. That is the important part of it. In fact, that idea was not belong to him. That idea was belong to Hertz. Hertz, you know that he's the inventor of the electromagnetic wave. After he invented the electromagnetic, or discovered, let's say it, he discovered the electromagnetic waves. He started experimenting with them, and he realized that the electromagnetic waves have a tendency to follow the conductive surfaces. For example, right now we are using waveguide to guide the electromagnetic energy to any point we want. Waveguide, combining into directions and leaving around it, and free to go in one direction, and we are controlling the direction it will go. And also coaxial cable. Again, there's a wire in the middle, and there's a surrounding plate around the nutter, and electromagnetic waves goes around the wire. In a way, you are braking or steering. You can steer the electromagnetic waves, and also the wire itself has a conductive surface. If you send a signal, if the high frequency signal in the wire, that the energy of that signal, it doesn't go through the wire. It goes near the surface of the wire. In fact, in two ways you can calculate that one. Either you can use the voltage and the current equations, or Kirchhoff equations, we call it, and also you can calculate the electromagnetic equations, because the current creates a magnetic field around it. Since the signal is changing, current is changing. The changing magnetic field creates the electric field perpendicular to it, and it flows parallel to the wire. The interesting thing in TWT, when he realized that electromagnetic waves have a tendency to follow the conductive surfaces, he took 40 meters of wire, and he made a coil of 1 centimeter, 1.6 meter long helix. He showed that the interesting thing, electromagnetic wave. Let's see. The electromagnetic wave follows the coil, goes through the rings, but with the speed of light, it follows that one. But when it's following the coil, its direction in the axis of the coil or helix, in the z direction, is slowed down. There's a simple equation over here. That's the reason I want to. It's the only equation I will show you. When he starts from this point, comes to the other point, 2 pi rotation, the coil is a little bit moved further. This 2 pi r the radius, and electromagnetic wave moves with the speed of light at t time. Within this t time, it moves in the direction of the axis. If you use these two equations, if you remove it, you can see that the phase velocity of the wave is less than the c, because this expression is 2 pi r over d is greater than 1. Therefore, the phase velocity, what you call the phase velocity of the wave, is less than the c. It can be 10% of the speed of light, or 70% of the speed of light. It's up to you, your configuration over there. Two factors determines that. One is the radius of the coil, the other is the pitch. They call it the pitch, the separation of the rings in the coil. This the distance determines it. We have done it, and also the interesting thing over here, there is a component of the electric field in the direction of the axis. That component of the electric field in the direction of the axis moves with the phase velocity. That's the important thing. Hertz didn't further. It just showed that the electromagnetic waves moves in the direction of z with the less than the speed of light. Kampf used that fact. Kovner he sent the electron beam in the direction of the z-axis of the. What is that? Show you. Let me show you later. So he come with the basic construction. There's no this one less. This one is much better. He come with the structure. This is the helical structure over here. Input is given from this part, and the other part, the output is taken. And there is a heater, there is a cathode, there is an anode. Cathode anode potential accelerates the electrons, and the electrons moves in the axis of the helix, and the magnets assures that one. All the electrons goes in the axis of the helix. There's attenuators preventing the backward propagation, and the electrons' speed is equal or near the electromagnetic waves speed in the z direction. They interact with each other because this is the speed. This is the action of the. Let's see. This is the axis of the helix. There is an electric field over here. This electric field at this point oscillates back and forth all the time. But at the same time, it moves. Because the traveling wave, with the phase velocity, it moves. If the let me show you this way. This is the electric field in the z direction along the axis of the helical helix. You can see that this wave is moving in the z direction. At one part is a positive in the z direction, and the other part is a negative in the opposite to the z direction. If the velocity of the electrons is greater than phase velocity of the wave, it's a decelerated. It comes over here, for example, this one, electric field applied in this way, the force is applied in this way, the electron decelerates, so therefore loses its energy in the form of electromagnetic wave. If the speed of electrons less than the Vp, because the electrons, due to thermal emission, there is an average speed, velocity, and also variations around it. Average velocity is determined by the cathode anode potential difference, but because of the thermionic motion, there are extra velocities they have. Therefore, average velocity is not the exact velocity for the electron. Every electron moves slightly with different velocities, either higher or lower from the average velocity. Therefore, the bunching occurs here, as you see, in these regions coming in the continuous beam, and after a few cycles, bunching occurs. Then it moves together when the velocity of the electrons, average velocity of the electrons is equal to or nearby the phase velocity of the wave, moving wave, and the bunch occurs usually in the decelerating region, Therefore, electrons all the time loses energy, and all the time interacts with the C there, C, let's call it C, electromagnetic wave, and amplifies it. Because since electrons are accelerated, decelerated or accelerated, they emanate or they release electromagnetic waves, photons. They release photons to the 6th power of the acceleration. This is the fact they utilize it. There is one important element over here. This is called the coupled. Of course, this input and output coupling over here, there should be impedance matching. That's important. Otherwise, the waves will be reflected back to the system. To get the electromagnetic waves, there should be impedance matching over here also too. There is a collector over here. The electrons, this multi-stage collector is important. The electrons should not come back or scatter back to the cavity, back to the helix structure, because it harms helix structure. Therefore, there is a multi-stage, they call it. There's a configuration. Electrons always scatters forward, and also they use that energy back to again. Therefore, the productivity of the system goes up to 70%. That's the interesting thing. This is the important thing. That's the principle of operation there. All this happens in the vacuum, of course. There's the special windows over here to prevent the air coming to it, and you can take it in a coaxial cable or a waveguide. Over here, there's a special window, what they call it. This slow wave structure, it doesn't have to be helix. It should be periodic, continuous. There's another way of doing it. There are many other configurations for it that people are exploring to improve the productivity, TWTA, but it has to be periodic. It could be semicircles connected to each other in one way, and it's also the periodic structure, semicircles connected to, and it serves the same purpose then. But corrugated periodic structure, what you call it, they call it. The gain is very high, 40 to 60 decibel. 40 decibel means 10 to 4, and 60 decibel means 10 to 6 times. It amplifies the amplitude. That's called type gain. Efficiency could be higher depending on the structure and the collector. Can higher output powers changes to kilowatts from watts to the kilowatts, because there are different applications. For different applications, you need different power. Sometimes, for example, for telecommunications, for the cell towers communicate with each other with microwaves. Now, they are not using the TWTs right now, but they need that 10 watt power. Every 15 kilometers, cell tower is built, because the microwaves doesn't go further depending on the ranges. Depend on the power output. In the steels, you cannot go higher, cannot operate with the higher power. This is comparing the magnetron, glycerin, and traveling wave tube in terms of gain, efficiency, bandwidth, output power, and I don't know it's related to that in use. The important usage of the TWT is space telecommunications and the military applications. Let me tell you one thing that's interesting. You know the Voyager 1? Around the 70s, it's sent to discover the solar system. Right now, he left the solar system, millions of kilometers away. It's using TWTA amplifier to communicate with the Earth. That's interesting. And also, James Webb Telescope, the JWST, what they call it, taking the pictures of the early universe. It's affecting our understanding of the universe. And also, it's using TWTA amplifier to communicate those pictures to the Earth. They get an energy from the either Voyager 1 we're getting its energy from the nuclear battery. But the James Webb Telescope getting its energy from the sun. And all they are using WTA. High power and high gain applications of microwaves becoming more and more important because of the drones introduced into the warfare. Other colleagues was here. He showed that the four massive developed four to wipe out all the drones. The drones swarm. It's not even like the swarms, millions or thousands of drones, hundreds of drones that are connected. We cannot shoot them single by trying to shoot them using the microwave radiation. They can be that way. Microwaves are important in our aspect. In medicine, as they use. For example, if you go to for cancer treatment, if you need a radiotherapy, they are using microwave to generate X-rays. Because even it's being used in the accelerators also, in the CERN and in other places to accelerate the electrons. There is another mechanism to accelerate the electrons. They are using high frequency, high power microwaves. There are cylinders next to each other and connected to the microwave signal. The electron passes and passing from cylinder to cylinder. Experiences electric field and experience. Therefore, microwave. I remember in Sweden, they were making a transformation source. They were doing the linear proton accelerator. At the time, I was in TÜBİTAK. We were trying to get involved. They asked us to come up with the klystrons, hundreds of klystrons. So, we were trying to get the knowledge of klystron construction to Turkey because you don't manufacturing the klystrons. There are companies in Europe. We are planning to collaborate with them and we learn about the klystrons. You will see the klystrons on tomorrow. Tomorrow. Klystrons are also important. You know, the applications, especially for satellites. I thought its advantages were wide. I gained information that I think this advantage is bulky, is heavy, right? Not too fragile, especially requires high voltage power supply. You need a high voltage power supply. And also limited lifespan compared to the solid state amplifiers. Later on, quantum mechanics came up with the solid-state based transistors and amplifiers, like arsenide and gallium nitride based. Therefore, right now, in most of the applications, the low power applications, solid-state amplifiers are being used. But high power applications for military purposes or space communications, you need the microwave amplifiers for defense. Do you have any questions to ask?
In middle school, I was in middle school, I read on TÜBİTAK science journal. Nuclear radiation affect semiconductor devices, but TWT or lamp type communication system doesn't affect with nuclear radiations.
Of course. That's the Voyager 1. They were using the solid-state type amplifier for communications. When it exits from the solar system and it faced with the radiation coming from the space, the interesting thing, solar radiation coming from the sun and the radiation coming from the space,
Cosmic radiation,
what we call it, they collided, and in that region, the amount of the radiation higher than the other parts. When it's passing in that region, Voyager 1 malfunctioned, lost the communications with the ground stations. And they switched to the TWTA amplifier and they established the communications. Because solid-state amplifiers are very susceptible to the radiation. Therefore, they need a kind of shielding. Regardless how much you shield it, still you will have some residue of it.
For example, lead, yes. So very heavy, very it's not important for
best screening material is the lead. We have the same problem for the satellites right now. Yes. The satellites in the radiation zone. Our atmosphere or the magnetic field prevents us from the most of the radiation coming from the sun. Still, there's the radiation is coming from the sun. If you stay in the summertime, especially at noon, you get the sunset. Okay, sunburn. You will get the skin diseases, skin cancer. This is the radiation coming from the sun.
Thank you.
Therefore, this system, you see the picture, there is not any part. Now, look at this. You cannot see any part that will be affected by the radiation. Just the wire, cathode, anode, maybe cathode in the long term, if you bombard it with the radiator by the radiation, maybe get a little bit of harm, but beside that, it's a very robust system. Radiation hardened, they call it.
May I ask a question? I see that the weight of TWT is a weight device, and recently we have I searched something in IEEE papers, and I have seen that miniature TWT are coming. So what can we say about weight of TWT, mini TWT?
The problem, the weight of the TWT comes from, you see the heater part, and there's a auxiliary power system also needed. It's very heavy. But itself is not much heavy. You can put in a glass, or you can put in a
vacuum system.
But as you said, the people are trying to make it as little as possible. There was a, I don't know if I can.
New technology, high power supplies are smaller than
Yes,
these
yes.
previous.
I searched something in IEEE and I saw a paper that weight, for example, a design is shown in IEEE. It says that weight is less than 200 gram.
100 gram.
Yes, that's
Oh, that's
interesting. Yeah.
Space activity.
KA band. Yes, maybe space TVT.
Systems for radar applications, all systems.
Oh yeah, exactly.
Requires the high power source vessel.
In satellite systems, there are, I think, 24 TWTs inside the satellite. Because these cascaded, because they have a lifetime, when they go down and another one comes to.
The lifetime is limited by the usual cutoff lifetime.
Yes,
That is important.
a very
Yes.
important part.
Yes.
I couldn't make it work. There is a YouTube video. Takes the TWT, disassembled it. It shows all the parts together. You should watch that. It's very inspiring. Unfortunately, I couldn't bring any. I wanted in this workshop to see what we are talking about. The Electron is a magnetron, and also a TWTA could have been shown to you if we have brought it to you. But we didn't have that chance. Maybe in the next time, inshallah. And if you organize that, another one will be organized in the future. So I will make sure that you will see the magnetron, not the pictures on it, but you will touch it with the
Yeah.
Magnetron.
In the oven, everybody you can see, I think.
Ama they cannot open them. They cannot open them. That's good. I like to show them that you don't look today. How simple it is. That's all.
Okay. Thank you. You, Professor Türköz, for this nice talk. I think it's very good to enter story.
If I understand.
No. Now let's take a break, 15 minutes, and then continue the other section.